All right. So generally, when a network is designed, it is designed with a three-stage hierarchy: with core, distribution, and access. Access is the part of the network where the user actually connect to, and then the distribution is the part of the network where we create redundancy. Right? So if let's say the link from switch A1 fail, that link going up to B, then there is another link going over to D2. So that switch still has access to the rest of the network. Right? So we create that redundancy of what the distribution layer. Also, things like routing and restrictions would be done at the distribution layer. So, well, in this case, we are just showing some normal layer 2 switch, but generally we would have like layer 3 switches here. So you want it to be really fast. And then the core now is the center of the network. Um, if we are linking like two networks, then that's when we go through the core.
Oh, yeah, I remember. It's a layer three switch. It's like a built-in router thing, built-in router.
Yes, it's a switch and router combination.
Okay, okay.
Right. So in this case now we're not showing the core, so we just have the distribution and the access section. Now, in a case like this, as you see, we have two switches up at the distribution section. Right? Now, with spanning tree, we may want to have two different routes. So we may want to have B1 be a route and B2 be a route. Generally, spanning tree does not allow that, right? The original spanning tree, you only had one route. But with rapid spanning tree, you could actually have two routes. So, and earlier I had mentioned in the previous slide that sometimes network administrators choose which switch is going to be the route. So in cases like this, the network administrator would actually make the distribution switches be the route. Because if they don't, then they have no idea which one will actually become the route based on the election that the switches will do. The preference is that the distribution switches become the root. So once we have the network set up like this, then in most cases we make the effort to ensure that at least one of our distribution switch become the root. All right, so this is showing us now under what conditions we could have two different routes. So we have two VLAN, right? So assuming the network is using multiple VLAN, we could say, okay, for VLAN 1, we're making switch 1 root. So switch 1 is now the root switch or the root bridge. And then for VLAN 2, we make switch 2 root bridge. So what that does is it allows the traffic to be to take up to have less bottleneck. That's one thing. Let's take a look here. Um, let's say this switch at the far, this PC at the far right need to communicate with this PC on the far left. Right? So generally, it is going to send the traffic up to the route, and they say D1 is the route, and then it comes down. Right? But if that is for VLAN 1 traffic, then if we have VLAN 2 traffic following the same path, then we now have two sets of traffic traveling the same path, and that could cause bottleneck. So what we may want to have happen is VLAN 2 traffic travel a different path. So let's say this PC in the middle here is in VLAN 2. So in that case, if we designated B2 as a route, then those traffic now would actually go up to B2 and go across to get over to switch A1 and let's say possibly this PC right here. So as you see, the VLAN 1 traffic and the VLAN 2 traffic is traveling two different paths. Therefore, we reduce the potential of having bandwidth issues because they're not on the same path. That makes sense?
Yes, it does.
Okay. So that's one of the reasons why we would have two different routes. So each VLAN node could have its own root switch. Now, this is kind of a historical timeline for the different VLAN mechanisms that are used. So initially, what existed was just STP, plain old spanning tree protocol. Then the IEEE came in with PVST, which is per VLAN spanning tree. Right? Cisco called it per VLAN spanning tree plus. Later, there was rapid. Oh, sorry. This is Cisco came up with per VLAN spanning tree plus. The IEEE came up with the concept of rapid spanning tree. So when they built rapid spanning tree, they also created something called multiple spanning trees. So you had rapid spanning tree and multiple spanning tree. Then Cisco came up with a rapid per VLAN spanning tree plus. So just showing the timeline as to how these different spanning tree protocols came about. We'll look at the details later and we'll see some of it here. So spanning tree is based off spanning tree. So and just to note, spanning tree was not created by Cisco. It's created by a company called Deconet. So um, it was called common spanning tree, as in there's just one spanning tree. So if you had 10 VLAN, it was just one spanning tree, which means all the VLANs would have the same switch as a root, which is where we would end up with bottleneck. IEEE call that the 802.1D. That's the IEEE standard for it. There was no specific configuration. You just turn it on or you turn it off. Right? So hence why we have NA here. As a feature on the switch is either on or off. So when Cisco came up with the per VLAN spanning tree plus, it was really based off the original spanning tree.
You saw the record, right?
Yes, I did.
Okay.
Yeah. Uh, so per VLAN spanning tree plus was based off the original spanning tree. It was also it was one spanning tree per VLAN. So every VLAN now had its own spanning tree, which is a huge improvement. It was still 802.1D. In terms of the configuration, when you're configuring the switch, the keyword you use to indicate is PVST. So when you're configuring spanning tree and you use the keyword PVST, it meant per VLAN spanning tree plus. So when IEEE came out with rapid spanning tree, it was completely new. So it was based off rapid spanning tree, the new protocol. Um, However, it was still one spanning tree for the entire network, right? So it was using a common spanning tree. The IEEE code for it was 802.1W. Again, there was no configuration. It was just something you turn on or turn off. Then Cisco came up with Rapid per VLAN spanning tree plus, and it was based off the IEEE's Rapid spanning tree. Now, this was one spanning tree per VLAN, and the IEEE code for it, 802.1W. And when you're configuring the switch to indicate the rapid per VLAN spanning tree plus, you would type the code rapid-pvst. Then the IEEE had multiple spanning tree protocol, which is based off the rapid spanning tree. And in this case, you could have one or more spanning tree um, for the network. Now, it wasn't a per VLAN thing. It was just you could do multiple spanning tree in the network. And then it was called 802.1s. And the keyword when you're configuring it is MST. So here is what is used now to allow us to have the ID for the spanning tree. So before we would have talked about the spanning tree priority and then the MAC address, and those two things created the bridge ID. Right? Now the priority is a 16-bit number. Right? So 2 bytes, which is 16 bits, which meant we had the possibility on a network of creating um, 65,536 different priority levels. Right? So as one switch could have priority 0, next have priority 1, up to priority 65,535. And then, of course, there's the MAC address. Right? So all of that would now be the bridge ID. The issue with this is that there is nowhere in here to identify the VLAN, and because of that, that is why we only had one spanning tree for the network. So how they had actually fixed that is they split out the 16 byte for the priority, and they said, okay, let's just use 4 bits for the priority. So out of the 16 bits, they only allocated 4 for the priority. Right? And then the other 12 bits was used now to represent the VLAN ID because VLAN is 12 bits. So now we could easily identify the priority and the VLAN, and that will allow us to have um, a different spanning tree for each VLAN. Now, I, by doing that, there was an issue, right? The priority being 16 bits gave us 65,536 levels. If we make it 4 bits, we could not get that many levels, right? Because with 4 bits, the amount of levels now went down drastically to 16. It was just 2 to the 4. So 2 to the 4 is 16. So we could only have 16 levels now, while previously we could have 65,536 levels. So in order to make this new method compatible or backward compatible with the old one, what they did is made the levels in jumps or graduations of 4096. So the first one 0, the next one 4096, the next one up is going to be 2 times 4096, and so on and so on. That making sense?
Yes, yes.
Okay. Right. So that's what they did in order to allow it to be backward compatible. So this slide here is showing us well, more detail about how we got it to be backward compatible. So on the left side here is showing us the new graduations, and on the right side is showing us those new graduations in binary format. So typically it would have been 16 bits like what we have here, and then all of the bits could have been changing. But to let it work, they said, okay, let's just work with only the first 4 bits rather than all 16 bits. So only the values in the first 4 bits will be changing. So as you see, when we change this bit, that worked out, when we convert this number now to decimal, it worked out to 4096. And when we went to 0010, that went to 8192. When you went to 0011, followed by all those zeros, it went to 1,000 12,288, and then just continuing on that process. So instead of changing all the bits, we only change the first 4 bits to get the graduations being in the range of 4,096. All right. So now the bridge ID is going to be the priority, which is really just 4 bits now, right? Because we're only using the first 4 bits plus the system ID, which is going to use to represent the VLAN. Right? So VLAN ID inside here. So note we're saying now, if we had changed the last 4 down here and have 1001, that would be 9. So it's actually representing VLAN 9. So combining the priority and the VLAN is what we're showing down here. So we have the priority and the VLAN. Alright, so Ether channel. Now Ether channel is the name Cisco gives to grouping ports. So when we group the ports on a switch, Cisco call it Ether channel. Now it's important to note that is Cisco call it Ether channel, right? Because other companies will group the ports on the switch and don't call it Ether channel. They may call it channel bundling, or Microsoft call it NIC teaming. So different organizations call it by different name. Um, Cisco call it Ether channel. The general name for it is port aggregation. We're just aggregating several ports together. So how do we do that? First of all, you would need to type this command, and this is done at the configure terminal global configuration mode. So it's a channel group 1 or whatever number you choose to start the configuration. Key thing to note is whatever channel group you do on one switch, it doesn't have to have the same number on the next switch. The numbers can vary. So we add the channel group number, which is that. And then step 2, we use the same number for all commands on the same switch. So every time you're configuring the ports on switch 1, you have to use channel group 1. If you start with 1, you have to just say channel group 1. If you go to channel group 2, it's a different set of ports you would have been configuring. Make sense?
Yes, yes.
Alright, good. Now, at the second stage, we can now determine the protocol that allows these channels or these ports to work together. There are 2 different protocols. There is the one that Cisco uses, which is PAGP, which is Port Aggregation Protocol, and then there's the LACP, which is Link Aggregation Control Protocol. The PAGP is Cisco proprietary, and the LACP is one developed by the IEEE. So we can use either one, but just know that whichever one you are using, you have to just use that one all the time for all the ports in that channel group. So if we're using the Cisco proprietary method, this is how we would do it. We would say channel dash group and the channel number, then mode, and we would say desirable. Right? Now desirable means we are telling these ports that they must seek to become a channel group. They must actively seek to become a group. If you do this on one switch, and the other switch that they are connecting to, you have the option of saying desirable or auto. Desirable again saying we want them to we want them um, to seek um, to become I lose my train of thought. Yeah, we want them to seek to become a group together. If we say auto, it's saying they are not seeking to become a group. However, they will follow the direction of the other side that they are connecting to. Right? So if the other side wants to become a group, they will. If the other side does not, then they won't. Make sense?
Yes, it does.
Okay, so that's the Cisco specific one. For the
Okay.
IEEE section, that's one down below now. This is the IEEE method. So IEEE would use active, and active says the ports are seeking to become a group. And then on the other side now, we could choose to make it active or passive. Active, they're seeking to become a group, or passive, they're saying, well, we are not seeking to become a group, but we'll follow whatever the other side says. So we have the two options. Now, you could not on one side say desirable and down on the other side now you go and say passive because that's two different protocol and it would fail. That makes sense?
Yes, it does.
All right, good.
Mhm.
All right, so once we have our channel group set up, if we want to verify that it's working, we would type the command from our enable mode. We would say show ether channel followed by the number and then port dash channel. And the output looks like what we're seeing here now. So the output would have starts out with the number as you see here. PO1 is port channel 1. This and the word intend to change, and this is one thing I don't like with ether channel. They just keep changing the number. So here they call it ether channel. Down here they're calling it port channel, and on the previous slide it's called channel group. So when you're configuring it, it will be the channel group. When you're doing the verification, you would say ether channel, and inside the verification, the output says port channel. But they're all referring to the same thing. So that's something you have to keep in mind that you have these different terminologies, but they're all referring to the same thing.
Okay.
Yeah. All right. So um, the age here is telling you how long ago it has been configured and up and running. So this is saying 0 days, 0 hours, 4 minutes, and 4 seconds. It gives us the logical slot and port. Um, so this is saying the slot is 16 and the port is 1. So the port here is this port up here, and the 16 is the actual physical port on the switch. And we are using two ports, so the starting one would have been 16. Alright, so let's see what else. The protocol is using PAGP, which tells us that we are using the Cisco method. Um, and down towards the end here, we see gigabit Ethernet 0/1, gigabit Ethernet 0/2, and they are set for desirable. And they are both on switch 1. So this is on switch 1. So this is kind of telling us what happens with the port channel. Now, when we set them up, right, it allows for load balancing, meaning all the traffic going across it will not use the same interface. So some traffic is going to use interface one. In this case, we are saying we have four interfaces in the port channel. So some traffic go over interface one, some over interface two, some over interface three, and some over interface four. So that no one interface is being overloaded with traffic. But the switch still sees the port channel as a single unit. So let's say these were, oh, another thing to note is that we cannot put ports into a port channel or ether channel unless they are at minimum 100 megabits per second. So a 10 megabits per second port could not be placed in an ether channel. So so in that case now, if these were all 100 megabits per second, then the switch would just see it as a single port that is now 400 megabits per second in bandwidth. Got that?
Yes, yes.
All right, so ether channel load distribution. So this same load distribution that I was talking about here, we can determine how the load distribution works. And there are several methods. So we can make the determination by the source MAC, the destination MAC, both the source and destination MAC, source IP, destination IP, source and destination IP, source port, destination port, and both source and destination port. So let's talk about what that means when we say these things, right? So if we, in configuring it, we say we want the load balancing to be based on source MAC. What we're saying here is the MAC address of the sending device is what is going to be used to determine if a new interface within the ether channel is to be used to send the traffic out. With me on that?
Yes, yes.
Right. So as long as the source MAC address, the MAC address of the sending device doesn't change, we are going to use the same interface to send the traffic out. But once the source MAC address change, then we would change now to a different port, a different interface to send the traffic out. So that's what it means. And a similar concept with the destination, as long as the receiving device is the same, we will always be using the same interface on the switch. If the receiving device change, then we change the interface on the switch. And even though I say we, it is the ether channel software going to be making that decision. So that's how these things work. And of course, as you see, the MAC address is at layer 2, the IP is at layer 3, and the port at layer 4. So the decisions are made at the different layers based on
Okay.
the load balancing method that we choose.
Mm-hmm.
So here we're showing the source MAC situation. So we have sent three different frames, all of them having the same source MAC address, right? MAC1. So in that case, they all go out of the first port in the ether channel. Once we change the source MAC, so in other words, it's coming from a different sending device, then it moves to a different um, interface in the ether channel. And again, we change down here, so we are now Mach 3, so it's a different sending device. So again, it changes the interface that the data goes out of. Right. So um, the discussion that as we go forward, we're going to be looking at using four different interface in the channel group. So in this case, we're using gig 1/0/21 up to 1/0/24. Now, bear in mind that it don't have to be the same port numbers on either side, right? Even though we have the same port number in this um, diagram, but they don't have to. So up here, where it says 1, it doesn't have to be 1 over here. So this could be 1, this could be 8. Over here, it could be 21 to 24, and over here, it could be 15 to 19. They just don't have to match up. Right. So if you have configured Ether channel and you want to find out how the load balancing will work, but you don't actually want to send any traffic. Say, I mean, you could test it by doing pings, right? But let's say you don't want to do that. You just want to use the diagnostic tools of the switch to test it. Then you could type this command: show Ether channel load balancing. And the switch itself now would tell you how the load balancing would work. So it tells you here that it's using source mark, and it tells you based on different protocol. So even though we're using source mark, we could have been using source mark for IP and something else for non-IP, and something else for IPv4 and something else for IPv6. But it's telling you that we are using source mark for non-IP, source mark for IPv4, and source mark for IPv6. So we're just using source mark. So here now is where we're doing a test. So the command test ether channel load dash balance interface PO1, which is the ether channel MAC, and we have a source MAC address. So this is a source MAC address and then a destination MAC address. And at this, once you enter the destination MAC address, you hit your enter key, and then this is the output that the switch will give you. It says would select gig 1/0/22 of port channel 1 or ether channel 1. So it's telling you which port it would use or which interface it would use to send traffic out. Now, for our second test, we're using the same source MAC address, but we have changed the destination MAC address. And note the output, it says would select gig 1/0/22. So it's the same interface. And that is expected because we are using source MAC. So source MAC says we will only change the outgoing interface if the source MAC address changes. Make sense?
Yeah, yeah.
Alright, so in this case now, what we're going to do is change the source MAC address. So before I even look at the full command, let's look over here. You notice we have 0200, 0000, and down here it ends with 002, 0002, and down here it ends with 0003. So we're changing the source MAC address. Right, so let's look at the full command. Test ether channel load dash balance interface PO1 MAC, and this is our source MAC address, which ends with 0001, and then our destination MAC address. And then it says would select gig 1/0/22. So this is the interface it would use to go out. Our next test Test ether channel load dash balance interface PO1 MAC, and we change the source MAC address now to end with 0002. The destination MAC address is the same, and notice what the output says. It says would select gig 1/0/24. So instead of 22, it has switched now to 24. See that?
Yes.
Right. So by changing the source MAC address, the switch is telling us that it is going to use a different interface, still within the same ether channel, but a different interface. Alright, so in this case now, we have changed the load balancing mechanism, and this is how we do it. So we say port dash channel load balance source dash EST map. So a source and destination map. So we are changing how the load balancing works now. So instead of just source map, we're saying it must be based on both the source and destination MAC address. So it tells us, sorry. So right here now, we are doing the show. So we say show ether channel load dash balance, and it tells us source dash EST, which is destination map. So it's using both of them. And down here, it further clarified that it's for both non-IP, IPv4 and IPv6. Note how it is written though. It says source this XOR, right, which reads exclusive OR destination MAC. So for both source and destination, this is how it's written in the output of the switch. So let's look at a test. So we say test ether channel load dash balance interface PO1 MAC, and this is our source MAC 0200 0000 0001, right? And then our destination now is 0200 followed by all ones, and it tells us would select gig 1/0/22. So that is the port it would use, or the interface it would use to go out. Now in our second test, what we have done in the second test is to change the destination MAC address. So the source MAC address remains the same, but we have just changed the destination MAC address. And you would see it here, what we have done is just put a 2 at the very end. Right? So at the very end we had a 1 up top, down here we have a 2. So the output says would select gig 1/0/24. So it would change the interface, right, because it would only remain the same interface if both the source and the destination MAC addresses remain the same. Make sense?
Yeah, yeah.
Alright, so I think we're at the last slide. This is the last slide in this set. Alright, so any questions?
No, not now, no.
Okay, alright. So this is the third one now. So this is looking at subnetting. So we're moving away from spanning tree and rapid spanning tree. I want to just draw your attention to something. Remember, did you download the sim for the labs?
Yes, yes.
Okay. So let me just get it started here. Is what I want to, what I recommend is that you, as part of your review, that you use the sim, right? Because
Okay.
these things that you're going through are going to be in the labs as well, so it would help to bring them out. So this is chapter. We just finished chapter. Well, let me just look back. That would have been chapter 10. So let's bring up the lab. Skill builder. So configuring. Let me get this. You might be seeing everything on the screen, but I am not because my monitor is not showing me the entire window. So I have to make these things a little smaller.
Okay.
All right. So let's see this one. I just want to see if it mentions which chapter. No, it doesn't say which chapter. Alright, it's not saying which chapter. I was hoping it would have been indicating which chapter. So you, but it tells you over here the detail, right? So when you
Yeah,
click,
yeah,
so you can, I'm just going to go through and see if there's any that mentions things like spanning tree. So you know that you could use that one. Just a sec there. In this lab, you see how to show commands to understand. Okay, so that's not it. You see, let's show commands again. Let's use show commands down here now. This is to configure IP address. This is to configure IP address on PCs and switches. This is to configure a switch so that it can communicate using IP. Right. So these would have been like for the earlier chapters, between somewhere within chapters 1 and 8.
yeah, yeah.
So let's see, LAN switching now, CLI for the switch, switch CLI. So these are early part of switches. Switch CLI, setting passwords on switches,
Mm.
setting interface on switches. Um, let's see this one. Says in this lab you learn how switches build forwarding tables. So this is like the MAC address table on the switch. So we're getting close to the spanning tree thing. This is security on a switch. So this would be like setting passwords on port security. Yes. Configuration scenarios. Let's see what's in these. Switch interface and forwarding. Configuring VLAN. Okay. Troubleshooting. VLAN. Let's see more labs. Okay, so alright. I think we have exhausted all the labs inside here. I was looking to see if I see any that has to do with the spanning tree. But I didn't see anything specific with spanning tree. I would think though VLAN possibly would impact the spanning tree. I could I'll check it and confirm. But if any of them has to do with spanning tree, it would be the VLAN ones. Yeah. But I highly recommend that you use these labs, right? So you get the practice as well.
Yeah.
Right? Rather than just doing the reading alone.
Hmm.
Yeah.
So these lab actually show like oh start do this do that or you have to just jump in it.
No man, no. So let me pick one. Let's do like switch into no, let's do a VLAN.
Hmm.
So um let's say start lab. So it comes up like that. And it says this lab shows how to configure VLANs on a Cisco LAN switch. The lab begins with S1, PC1, and PC2 in the same VLAN. So that's S1, PC1, and PC2 in the same VLAN. It says due to default configuration of the switch, and therefore in the same IP subnet. During the lab, you will migrate PC1 and PC2 into VLAN 2 and 3. Change your IP address configuration and then verify that all three devices can ping each other after the migration to new VLANs. The lab begins with the required VLAN trunking configuration on both R1 and S2. Any passwords necessary for this lab, unless otherwise specified, is CS. So the password is CS. Now, where's my password? You will not see characters. Okay, we know that. So these are the steps. Confirm layer 2 and layer 3 details. This lab begins with, scroll. This lab begins with a working internet network with all devices in VLAN 1. Part 1 simply guides you through the process of getting familiar with the topology. So step 1, connect to SW1 from the simulator user interface and move to enable mode. So let's say connect to SW1, so you click on SW1. So now that you click on SW1, you are in SW1. Um, so it says connect to SW1 from the simulator user interface and move to enable mode. So we should move to enable mode. Now, because we have skipped some of the labs before, then
Hmm.
we should have known how to get to enable mode because it would have
Yeah.
been in previous labs.
Yes, lab. Okay.
Right? But of course, enable mode, you type ENABLE, and that takes it to enable mode. It
Hmm.
asks you for the password, and the password is
Hmm.
CS based on what we just read. And
Hmm.
so now we are in, this is user mode,
Oh yeah.
right? So enable and enter,
Hmm.
password CS, and we are now in enable mode.
Hmm.
Then we go to step 2. Examine the current configuration for any configuration commands on interface in 0/1 on switch 1 and FA 0/1 on PC2 and FA 0/2 on PC2. Record those interfaces subcommands in the text box below. So how do you get to the interface? Of course, you have to configure
Hmm.
terminal
Hmm. Hmm.
and then you do interface um, GI 0/1 and so GI 0/1 is what goes to goes to S1 PC S1. So it says examine the configuration um, uh, examine the current configuration for any configuration commands and interface. All right, so what I've just done is I've gone on the interface, but what it wants me to do is to see what is configured for the interface. Right? So if you want to see what is configured for the interface, then it's a show command you really need to type. So I want to do something like show IP interface GI 0/1.
Mm.
I did not activate show IP interface. So let's just do show interface then. And there I get the output.
Mm.
So and if I can get this window a little larger so we can see more. Yes. So that now tells me any configuration for the interface. So currently the interface of MT of 1500 bytes. The bandwidth is 100,000 kilobits, which is a gig. Um, Other than that, there is no specific configuration I see so far. Yeah, no specific configuration. The next one we want to look at is fast internet 0/1. So we say show interface FA 0/1. Take a look at the interface. So these are the things you would have been doing. Right?
Yeah,
Of course, we have skipped some labs, so certain things would have to know at this stage, but you would have learned them in the previous labs.
yeah, yeah.
Now you could actually check here on the right side here. You could
Mm-hmm.
check your answer by typing in the commands. So I'm just going to type show interface bi 0/1 and then to check answer. And it says correct answer. Right? The lab begins with no configured interfaces, which we saw there was no specific configuration.
Yeah,
And it says we could use the show running config command to display the currently used configuration. So, yeah. So you can use the correct answer thing to also help to guide you. Sorry, not the correct answer, the check answer, I should say. You
mm.
can check my answer. Yeah, so I strongly recommend that you try these labs. Right?
Yeah, yeah.
Okay. All right, subnetting. So introduction to subnetting, that's the first thing, first objective. Then analyze subnetting and addressing needs, make design choices, and plan the implementation. So those are the things we're going to cover here. So first thing, subnet plan document example. So they're saying if you have a network, you want to come up with a plan as to how we're going to assign IP address in that network. Right? So here's an example of a network where we have three routers and three LANs. So there's a LAN here, a LAN here, and a LAN over here. And of course, we have two wide area. So this is a wide area, this orange section. And then you have another wide area down here, the EONPLS, which is Ethernet over MPLS. So assuming we were given a class B network of 172.16.0.0, right? And it says the first three octets are equal, which means if the first three octets are equal, as we see here, it means the subnet mask that we're using is 255.255.255.0. Three sets of 255s, right?
Yes.
So this is the network that we'll be working on. So we have assigned over here 172.16.1, and then individual devices now can have numbers in the fourth octet. Inside this wide area, we're using 172.16.4, and then this router would have a number, right? Maybe 1. So 172.16.4.1, and then this one would have another number, 172.16.4.2. And we do the same for all the networks. So this section here is showing us the steps that we go through to do the planning. The first thing you want to do is to try and decide how many subnets you really have. Then how many hosts are on each subnet, and answer the question of, do you want to use just a single size subnet? In other words, every subnet is going to use the same subnet mask. Is that what you want to do? So those questions are actually detailed on this slide. So which hosts should be grouped together? That's a question you want to ask. So when you look on this, which one of these would be grouped together? So clearly we would group all the hosts over here together. We would group one from here with one over here. Agreed?
Yeah.
Right. So the next question is, how many subnets does this network require? So let's go back up. When you look at this, how many subnets would you say it need?
So, my black take a while. Hold on. No, three?
Five. So that's one right here where my mouse is. Then
Mm-hmm.
inside here is one for the wide area,
Mm-hmm.
and one for this wide area as well.
Mm-hmm.
That's three. And then one for this LAN.
Oh, never count those two.
Oh yeah, you have to count the wide area as well.
Mm.
Right. So we'll end up with five subnets.
Okay.
And then the third question says, how many host IP addresses does each subnet require? So if we look back on this, we must answer. We won't be able to answer the question based on what we have here because limited information is there, right?
Yeah.
But that's an answer we would normally want to get. Like how many hosts are going to be on the network? So how many hosts per subnet? Similarly, in the wide area, how many hosts per subnet? And similarly for over here as well, how many hosts per subnet? So those are questions we would want to have answered.
Mm-hmm.
And then the last one is, will we use a single subnet size for simplicity or not? So this is a decision the network administrator would have to make. Is it that you just want to use just one subnet size, as in one subnet mask, or you want to have different subnet mask at different subnets? So here's another network. In this case, we will need three subnets. So we need a subnet over here, a subnet for the wide area, and a subnet over here as well. Agree?
Yeah, with this now you could look and those as the host, the PG.
Oh,
ABC.
right. Yes.
Mm.
Yes. Right, right. So look at this one now. How many subnets you think we need?
One, two, three, four, five, six, seven.
Yeah, right.
Mm-hmm.
7 subnets. So we have
Mm-hmm.
4 sites, but we need 7 subnets.
Mm-hmm.
So this is going to a little more detail, but of course, from the diagram, we couldn't have figured this out. So we just have to work with what they have here. So they're
Mm-hmm.
saying over here, need 2 VLAN. Now, if you're going VLAN, then every VLAN must be a subnet, a different
Yeah,
subnet.
yeah.
So based on the VLAN that they have here, now how many subnets you think we would have? So looking at the VLANs now, include the VLANs in the code.
And the whole diagram.
Yeah,
Right. 12, 13, 14, 15, 16, and 2, 18, 22, 24.
24?
20. Well, I'll check again. It's 12 in the section, right? First section, right?
Yeah.
That is 12. Then between the switch and the router, it's 13. Between the router and the other router, 14, 15, 16. I said 2 VLAN, so 16 and 2, 18. Another 2, 20. Another 2, 22.
Okay. I get 21. And I think I see where the difference is though. Right here, you're counting this as a subnet by itself.
Yeah, yeah.
Alright. But it shouldn't be.
Okay.
Yeah. So because it's going to a switch and the rest of
Mm-hmm.
this are switches, so this should not
Mm-hmm.
be a different subnet.
Okay.
Yeah.
I get it. Mm-hmm.
Right. So that's how you get one more than me. So it's actually 21.
Oh, yeah. I see it clearly now.
Yeah. Alright. So they're saying here now, in this case, this particular part, they would
Mm-hmm.
want 50 hosts per subnet.
Mm-hmm.
So would have to now come up with a subnet mask that would allow 50 hosts. So we see over here as like a main site, a central site, and these over here are branch offices. But this particular branch need 50 hosts per subnet. Alright, so now that we have looked at this idea of the subnet, um, in terms of the IP addressing, we need to take a look at the IP addressing and say, how do we calculate these details about subnet? So the first thing we want to talk about is, in terms of how many hosts on this per subnet, how would we calculate that? And that's what we're showing right here. Right? So to calculate how many hosts we will get on the subnet, what we're going to look at is the host bits. And then we say 2 raised to the power of the host bits and subtract 2, and that tells us how many hosts we could actually get. Right? So if you just pick a number, let's say this is 4, 4 host bits. So the number of hosts that we could actually get would be 2 raised to the power of 4, which would be 16, and then we subtract 2, and that would be 14. You follow me? Follow that?
Yeah, yeah.
Right. So that's how we calculate the size of the subnet. Right? And when we say the size of the subnet, we really mean how many hosts on the subnet.
Mm-hmm.
Alright, so take this network here where Over on the left side, we actually
Mm-hmm.
have 200 hosts. On the right side, each of these networks must have 50 hosts. However, the requirement is that you want just one subnet size. So in other words, all the subnets must be at the same size. In a case like that, what you have to do is work with the larger subnet, right, or the largest subnet. So a subnet that have 200 hosts, we work with that and see what the subnet size would be. In this case, the subnet size will be 254, and we'll see shortly how that 254 works out. Now, because they say they want one subnet size, so if this one is 254, then we have to make all the others 254. Follow me so
Um,
far?
hold on. No, the 254 is the subnet size or the another subnet.
Say again, subnet size or?
254 is exactly what?
It is the number of hosts that we are saying based on the subnet that we are calculating could fit on that host, on that network.
Okay, okay.
Yeah. But they give us this restriction that they want to have one subnet size. So every subnet must be the same size. That's basically what they say.
Yeah, okay.
So if we make this one 254, then we just have to
Mm-hmm.
make all the others 254 as well.
Mm-hmm.
Now, the reason why this slide is here is to point out something very fundamental to us, is that
Mm-hmm.
using subnets, if you have a network and you have several subnets and you make them all the same size, you are likely not going to do an efficient assignment of addresses. Because as you
Okay.
see over here, we are wasting addresses,
Mm-hmm.
right? Because they only have 50 hosts, but we have assigned a subnet that is providing 254. So right now, 204 are being wasted on each of these subnets. You see it?
Yeah.
So um, while it would be nice and simple for us to just use one subnet size throughout the network, it is not an efficient method.
Yeah.
Right, so here is a better method. So we could actually do three different subnet size, which now means we'll have to have three different subnet masks. So over this side, I need 200, or we give them 254, so they have some room for growth. Over this side, they need 50, but we gave them 62. So in terms of wastage, we would have been wasting just 12 per subnet over this side, which is not bad.
Yeah.
So this is more efficient. It is not as simple. It's going to take a lot more calculation to work out, but it's much more efficient. So here's another example, and this is mentioning a new term here now, VLSM. So
Mm-hmm.
anytime we design a network that is using multiple subnet masks, we are actually using VLSM, which is variable length subnet masking. Right?
Yeah, yeah.
So on the left side here, we're using a subnet mask of slash 24. On this wide area, we're using a slash 30. And this wide area, we're using a slash 30. And over here, we're using slash 24. And down here, we're using slash 24. So We have answered the questions. I'm just going to scroll back up to where this all started. Right. So we have answered this question: number of subnets, how many hosts per subnet, and questions about should we use just one subnet size or multiple subnet size. Right.
Mm-hmm.
So the next thing we want to talk about now is choosing network, as in what network should we use? Should we use a 10 dot something or should we use a 172? Right? And if whichever one we're using, can we, having come up with the subnets, can we actually list the individual subnets? So that's what we're going to be looking at now. So we have moved from there, we have completed our analysis and we are moving into designing the subnets now. Cool?
Yeah.
So this is the designing of the subnet section now. So we want to answer the question of how do we choose a network and um, whether or not we're going to be using one mask, and if we use one mask or not, then we must be able to list the individual subnets. Alright, so here's the first step. In this case, we have two companies, and we could even see it as one company with two branches, right?
Mm-hmm.
And they have two different IP addresses, or two different networks being used. So they're connected, both connected to the internet. One of them is using a network of 1.0.0.0, the other is using a network of 2.0.0.0. Now this is quite fine because these are public IP addresses, right? And the public IP addresses are routed on the internet, and also they should be unique, meaning nobody else should be using the same public IP address that you are using. So we're okay with this. Now here's another case where two companies using the same IP address. Now this is a problem. It's a problem from two perspectives. The first one and the most obvious here is that they are private IP addresses because 10, the 10 network is a private IP address range.
Okay.
Right? And private IP addresses cannot communicate on the internet. No private IP address could actually send traffic to the internet. So as a result of that, we would need to use network address translation, which means these addresses must be translated to a public address. So it will appear to the internet as if it's coming from a public address. Right? Now this is typically what we are already using in our case. And I want to show you something just to demonstrate it, right? I'm going to bring up my browser. So my IP address. Then let's click on this link and it tells me this is my IP address, my public IP address, right? 207.204.64.220.
Mm-hmm.
I'm also going to bring up my command prompt now. So one step there. Here's my command prompt window, and
Mm-hmm.
I say ipconfig, and as you see right here, my private IP address is 192.168.0.7. So in the home, I have a private IP address, but this IP address cannot be used to communicate on the internet. So every time I'm sending traffic out to the internet, it is translated to my public IP address using network address translation. Okay?
Yeah. Yeah.
All right. So So that's what we're seeing in this case, right? As I said, there are two issues. The first one is that these addresses are private and therefore they have to be translated to network address, translated using network address translation to send to the internet. Right? Now, the second issue with these is that they're both using the same IP. So even if the IP address was public, they are both using the same IP address, which would end up being a problem because public IP address need to be unique on the internet. No two companies should be using the same public IP. So the NAT would still help in that case because you could translate one of them IP address to something else, to a different public IP address. And so on the internet, they would then appear to be using two different IP addresses. Okay?
Yeah.
So here are the listing for the private IP addresses. Now, in this case, we are not listing the actual IP addresses, we are listing the networks. And I'll explain the difference. Let me just close some of these windows. Close my lab window. Alright, so let me just get Notepad. Alright, so as we see here, we're using, it says for private IP, the network is 10.0.0. However, if we were looking at the IP addresses, we would have said 10.0.0.0 up to 10.255.255.2. That's the IP address range from 10.0.0.0 up to 10.255.255.255. But all of that is just one network. So, and that's what it's showing us up here, right? It's one network. So the 10 for private IP address, we only use one network. It's a class A network. And for the class B network, we have the networks are 172.16.0.0 up to 172.31.0.0, which is 16 different networks. If we were to write the IP address ranges, we would have said 172.16.0.0 up to 172.31.255.255. That would be the network, the range of IP addresses. With me?
Do that again.
Oh, so what I was looking at is based on the slide, what they're listing is the networks. So this is saying we have one network, which is
Mm-hmm.
10.0.0.0. But I was saying now, if we were to really list the IP addresses in that network, we would have to start from 10.0.0, which is the very first one, and then
Mm-hmm.
we go to the very highest we could ever get to, which is to have all the octets that were initially zero go up to 255.
Yeah. Yeah.
Right. So that now would have been listing all the IP addresses in the network, or the range of IP addresses in the network.
Right. Right.
And then we did the same for the class B, which is the networks, only the networks that are zeroing in on here, which is 172.16.0.0 up to 172.31.0.0. 16 different networks. But if we were to list the IP address range for the networks, it would be what I have here.
Okay, okay,
So this is the range of IP addresses.
okay, that,
172.16.0.0 up to 172.31.255.255.
okay, I get it.
Make sense?
Yeah, yeah.
Okay. And then for class C, again they're just listing the networks. And in class C, we would have been using 256 networks, which is 172.16.0.0, sorry,
Okay.
192.168.0.0 up to 192.168.255.0. Alright?
Yeah.
Now, for the different IP address classes, that's what we're listing here. For class A, the first 4 bits, sorry, the first 8 bits form the network, right? And then the last 24 bits form the hosts. So we have 8 bits, 24 bits. The blue section is for the network, the yellow section is for the hosts. For class B, we have the first 16 bits are for the network, and then the next 16 is for the hosts. For class C, the first 24 bits are for the network, and the last 8 bits are for the hosts. So
Yeah.
this just showing us how the networks are arranged. Concept of borrowing host bits. Now, this concept of borrowing host bits is what we use when we're doing subnetting. Right?
Yeah.
So normally we subnetting we would want to either get the number of hosts either increased or decreased. Right? And if we want it to be increased, we're going to borrow some of the subnet bits and use them as host bits. Now, I always like to explain that this term that they say borrow, as when you use the term borrow, it sounds like at some point you're going to give them back,
Mm-hmm.
but they are not going to be given back. Right? If you take them for the host bits, they are just going to be used for hosts. So, if we look at the arrangement, all of the bits must add up to be 32. So all of our network bits plus the subnet bits plus the host bits must add up to 32.
Still back to the amount.
Right.
Mm-hmm.
So if um, we reduce the host bits, then it means the subnet bits getting larger
Yeah.
or the network bits getting larger, one way or the other.
Okay, the network changed. Okay.
Yeah. So these are the rules.
Mm-hmm.
Right? If we want to find out the number of hosts, which is listed here as y, then what we would do is take the host bits, which is h, and say 2 raised to the power of h, which is 2 raised to the power of the number of host bits, and then minus 2. That's what we use to find out the number of hosts that we can get. Okay?
Yeah.
Right. Now, typically, when you are given the requirement, like a company says we want 10 hosts, you may not be able to get that number exact. Right? So what you are going to aim for is to get that number or something just a little higher. So if they say they want 10 hosts, which in this case it would be saying y must be equal to 10, then we need to work this formula so that we either get 10 or some number above. So for example, if we make H3, and I'm just picking a number, so it will be 2 to the 3, which is going to give us 8, minus 2 is going to give us 6, which is going to be lower than the 10. So we couldn't use 3, we'd have to have a larger number. So let's use 4. So it will be 2 to the 4, which is 16, minus 2, which gives us 14. They wanted 10 and we get 14, so we could work with that.
Yeah, so it must be equal to or greater than.
Right, which is what we
Yeah.
have here.
Mm-hmm.
Get it?
Yeah.
Alright, so similar thing for the network side as well. On network side, in this case, we're really talking about the subnet. So the number of subnets, which is really the number of networks they need, right? Because inside the network you're going to have the smallest network, which we call subnet, which is really shortened for subnetworks. So we're representing the number of subnets by the letter X. So to find the number, it is really 2 raised to the power of the subnet bits. Right? Now, let's say they give us something like, let's say they want 5 subnets, right? Then we want to have a certain number of bits inside here. So when we work out 2 to that power, it is either 5 or greater. So let's say we are done 2, right? We have 2 bits inside here. Then 2 raised to the 2 is going to give us 4. So that would have been less than the 5, so we couldn't use that.
Mm-hmm.
If we use 3, then 2 to the 3 is going to give us 8. So that could work, right?
Yeah.
So that's how we're going to work out these things, trying to decide on how many subnets and how many hosts we should have. Um, just to present a quick table so that we may not have to do these calculations. We can, if we can memorize this table, or
Mm-hmm.
be able to figure out this table quickly, then it makes things so much easier. So this side here is going to be the subnet side, and over here the
Mm-hmm.
host. Right? Because the subnet we don't need to subtract 2, it is only for the host section we need to subtract 2. With me?
Yeah, yeah.
Right. So if it's 1 bit, just a single bit, then 2 to the 1 is equal to 2.
Mm-hmm.
2 to the, over on the host side, 2 to the 1 is 2, but when we minus 2 we get 0. So that will be saying 0 hosts,
Mm-hmm.
and of course 1 subnet. Sorry, 2 subnet. I'm just going to skip a few. So let's say we go to 4.
Yeah.
Then on the subnet side, it is 2 to the 4, which gives us 16. So we could get 16 subnet if it's 4 bits. On the host side, using 4 bits, it's 2 to the 4, which is 16 minus 2, which gives us 14. Make sense?
Yeah, yes.
Alright. So, um, helping us to choose the subnet mask now, right? So, um, looking at class E network, where the first 16 bits are the host, and the next 16 bits the first 16 bits are the network, the next 16 bits should be the host, but we are doing subnetting, so we're going to have to split this host section now between subnet and host. So in this case, let's say we split it right down the middle. So we have 8 subnet bits and 8 host bits, right?
Yeah.
So to find out the number of subnets, it is going to be 2 raised to the power of 8. Right? So 2 to the s, but s equal 8. That gives us 256. Right? 2 to the 8th power is 256. The same thing on the host side. We have 8 bits. So 2 to the h, while h is 8. So that's going to give us 256. And then we subtract 2, gives us 254. With me?
Yeah.
Yeah. So if it is a case where the company really needed 200 subnets, then in this case, we would have given them an extra 56 subnets. Agreed?
Yes. Subnets. Yes.
Yeah. And then over here, if they needed 200 hosts, we would have given them an extra 54 hosts.
Yes.
Right. Now, to get the subnet mask, what we're going to do is just take a look at the network section and the subnet section. And you all the bits for the network section, we're going to represent those bits as 1 in the subnet mask. So
Mm-hmm.
actually take the IP address. This would be for the IP address, which
Mm-hmm.
would be this again for the IP address. But we're just going to look at the network section of the IP address. And when we're working on the subnet mask, we make all the bits in the subnet mask that associate with the network section. We make those bits 1. With me so far?
Yeah.
And then same for the subnet. So that part that we are using as the subnet, all the bits in our subnet mask, we're going to make them 1 as well. Right?
Yeah.
And then the section we're using for the host, in the subnet mask, we're going to make all those bits 0. And that's how we get our subnet mask. Cool?
Yeah. Yeah.
Right. So this then would work out to a subnet mask of 255.255.255.0.
Yeah.
Alright, and what we've done here is just write out the subnet mask, not the subnet mask, the different networks. Um, so, well, let's go back a little. Notice that said is a class B they're working with, right?
Mm-hmm.
So they have given you a class B address of 172.16.0.0, and this is the subnet mask that we just worked on, 255.255.255.0.
The subnet never calculate though. They just wrote it down, right?
Well, yeah, they never do the calculation, but based on
Mm-hmm.
this, all 8 ones
Mm-hmm.
is 255.
No, 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 not that. The 172 16 or something.
Oh, yeah, 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 yeah.
Mm.
They just wrote that down. So
Okay.
yeah, right. So they just say, okay, this is what we're using.
Yeah,
Let's
yeah.
pick it out of a hat.
All right, right.
Yeah. So 172.16.0.0 as the subnet number.
Mm-hmm.
Then the first address would then be 172.16.0.1,
Mm-hmm.
and then the very highest address would be 172.16.0. Well, let's put it over here. The broadcast is 172.16.0.255.
So they would either ID and broadcast like that with similar thing.
Right. So the subnet number is the same as the subnet ID.
Yeah.
Right? And then the broadcast. And of course, the last valid would be just 1 less than the broadcast. So if we subtract 1
Mm-hmm.
from this, we get 254.
Yeah, yeah.
Right. And the next network work out the same way.
Mm-hmm.
So we've just completed the second stage.
Yeah.
So the next stage now is to implement it. How do we actually implement it in a network?
Mm-hmm.
So one other thing you want to bear in mind is subnet is equal to location.
Uh-huh.
So each location will have a different subnet. Then we'll have to decide now, are we going to assign the IP addresses statically or we're going to use DHCP? And it could also be that we're using both. Some devices get IP address static and some using DHCP, right?
Yeah.
All right, so come back to the example we started out with. You remember this is the slide we actually started out with,
Yeah. Yeah.
right? So we now have our different networks. We have 172.16.1. So basically, they just pick some of the networks and use them. Basically, they're using
Mm-hmm.
the first five out of the set, right?
Yeah. Yeah.
So each location get a subnet, which is what they had said here, right? Subnet is equal to location.
Mm-hmm.
So now these locations, we could think of them as different things, right? It could be places inside a country, or they could be places on a continent, or places across the world. So
Mm-hmm.
they're looking at it from across the world. So they're saying, okay, let's think of like North America, Europe, and Asia, and then North America would have from subnets from 0 to 127.
Mm-hmm.
Europe would have from 128 to 191, and Asia would have from 192 to 255. And these things basically just is just a scenario they're building, so there's no calculation for it, right?
Right. Right. I figure.
So we're picking something out of the North America region because we're saying 172.16.1. If I just go back up, notice North America is 0 to
Mm-hmm.
127.
Mm-hmm.
So this is saying we're working in the North American region. Cool.
Mm-hmm.
Right. Now, remember, one of the things we wanted to determine is are we going to use statically assigned IP addresses, or are we going to do DHCP, or are we going to do both? In this case, we're doing both. So what we're going to do is the lower numbers, we're going to use those for the static, and then the higher numbers, we assign them to the DHCP pool. So things like our servers and our routers, we're going to give them static IP address. So they'll have IP address in the lower numbers. And then the client computers, individual computers, we give those DHCP, so they'll have IP addresses in the higher range.
Okay.
So that is why our server here would have 172.16.1.11. Our router interface would have 172.16.1.1. Over here, this router interface would be 172.16.2.1. And then the client now is going to get IP address from a DHCP server, which is, and this would be our DHCP server over here,
Mm-hmm.
which is now going to get 172.16.2.101, and this one down here, 172.16.2.102. Cool?
Yeah.
And that's the last slide.
Okay. So all for reading for me.
Yes. Um, yeah, so unfortunately, we have some slides that we haven't gone through. I know I missed out some
Mm-hmm.
part of it. I don't know if you too tired, or you want to take the time out, just look at another one?
We call it a day and all that.
Okay.
We call it a day. 4 hours
Yeah,
almost.
yeah, it is tiresome.
Yeah.
Yeah, I
We
know.
go through this about the slides
Yes,
and the recording and everything.
right, right. All right. All
Yeah.
right, let me stop the recording.